The Vedoretto lab project is not just a scientific curiosity, but a genuine attempt to get closer to nature's secrets. By understanding earthquakes for such proximity, we hope to unlock new dimensions in geoscience and geoenergies. And let me say that while the Alps might be a destination for people to escape, well, for us is a journey to understand the Earth better.
Welcome to Chelonia Podcast, a podcast about the use of scientific discoveries and of technology applications. We provide the best information on projects participated by Chelonia and many more. My name is Gabriella Bernardi. I'm a science journalist, and in today's episode of the second season, we talk about geoscience, computational geomechanics, and earthquake physics with Luca Dal Zilio, senior researcher at the Institute of Geophysics at ETH Zurich, and recently also winner of the Jason Morgan Award. Congratulations and nice to meet you.
My pleasure.
Professor, would you please briefly introduce yourself and tell us what is the Jason Morgan Award?
Thank you for having me on your podcast. So my name is Luca Dal Zilio, and I'm a senior researcher at ETH, the Swiss Federal Institute of Technology in Zurich, Switzerland. I grew up in a city called Treviso in Italy, which is really close to the world-famous city of Venice. And from a young age, I've been always fascinated by the planet Earth. I went to the University of Padova to study geophysics. This is the science of understanding of how our planet behaves and evolves from its deepest core to the ground beneath our feet. During my time at Padova University, I began a master thesis project with a fantastic supervisor where I use mathematical models and computers to simulate and study how our continents have changed and evolved in space and time. This experience was a transformative period for me. I realized I truly enjoyed the process of scientific discovery, formulating an hypothesis, crafting a mathematical model to understand this hypothesis, and constructing a framework to analyze the underlying physical mechanisms, and ultimately deriving intuitions that help to better understand the Earth evolution. Because of this passion, I decided to continue my study, and I went on to do a PhD at ETH Zurich. I got the chance to develop mathematical models and computer simulations to link the processes that control the slow deformation in the Earth crust and the very short but fast processes responsible for the generation of earthquakes. And after this, I moved to the United States for 3 years at Caltech, California Institute of Technology, in the sunny Southern California of Los Angeles. And there I learned state-of-the-art techniques to model earthquakes, earthquake physics. In 2021, I came back to ETH, and now I lead a team of students where we try to understand earthquake physics, specifically why earthquakes start, how they move across the crust, and what makes them stop. So recently I had the honor of receiving the Jason Morgan Award from the American Geophysical Union. This is an early career award for contribution to geophysics. It's an early career award because nominees are no more than 6 years past their PhD. And the award is named after the great scientist and pioneer Jason Morgan, who taught us how different pieces of the Earth move and interact, which are what we call today tectonic plates. Imagine our Earth's surface as a big puzzle, and each piece moving slowly. So Jason Morgan helped us to better understand this puzzle. Also, Jason Morgan provided a fundamental contribution to the so-called hotspots, which are not what we use in our phones today, but are these hot plumes rising from the deep mantle to the base of tectonic plates. And this mantle plume hypothesis remains a leading explanation for the formation of islands like Hawaii and Iceland. So from my side, receiving the Jason Morgan Early Career Award this recognition to my work, meaning that the geophysical community values your work. For this, I would like to thank the nominators of this award, mentors, colleagues, and also friends who have been instrumental in shaping my career. And at the same time, it feels like a responsibility and a starting point when I look at the future. It's a boost and a motivation force that will drive me to continue to seek this question and discover.
Very, very interesting, and congratulations again. But now, how your work help to understanding of earthquakes?
Understanding earthquakes is a profound challenge. It's critical to note that we don't possess direct access to data when it comes to understanding this natural phenomena. So earthquakes happen deep beneath the Earth's surface, typically at a depth of 5 to 15 kilometers. So unlike studying, say, a plant where we can observe it, touch it, and analyze it, with earthquakes, we are in a way operating blind. It's typically, we don't possess or we don't deploy instruments close enough to the rupture generating that can help us to better understand this process with the high resolution measurements. So we have indirect measures of seismic waves, for example, but the core processes, the preparation leading to an earthquake, they are hidden from us. So this preparatory phase is not just a matter of days, months, or even years. We are talking about processes that can span many years or even centuries. Now imagine try to understand something that has been developing for hundreds of years, deep below the ground, and you will try to understand the magnitude of the challenge that we face. So this is where my work comes in. So to understand and to overcome these challenges, we turn into the world of numerical simulations. So these are think of these simulations as detailed, sophisticated computer programs that allow us to recreate the conditions and processes leading to an earthquake. By using them, we can extend our temporal window, giving us intuitions into the stress conditions in the Earth crust and ultimately culminate in the occurrence of an earthquake. But the application of these simulations don't end there. We are constantly making hypotheses about earthquake, formulating theories based on the data we can get from various sources. Now this numerical simulation serves also as a testing for theories, for example, from laboratory experiments, where, for instance, tests that are done to rock samples that are centimeters in size, and then we try to upscale them and trying to verify and better understand how earthquakes happen when they occur on a large fault, on a kilometer fault in scale. So when a large earthquake occurs, for example, the recent Turkey earthquake in February, it's a race against the time to understand what happened. And here again, our simulations come into play. So with them, we can rapidly deduce crucial characteristics of the earthquake, how fast was the rupture, which fault was involved, and so much more. So, of course, now when we talk about this, I would like to address a commonly asked question: can we predict earthquakes? The straightforward answer is no, at least not with our current understanding and technology. But what we can do, thanks to this simulation, is test our various scenarios. By simulating different earthquake events, we can get a better idea of what might happen under specific conditions. And this ability to model potential scenarios is fundamental when it comes to seismic hazard assessment. So in simple terms, while we might not be able to predict the next big quake, we can certainly prepare better for it, understanding its potential impact and planning accordingly. So all in all, the realm of numerical simulations has been crucial in bridging the gap between what we know and what we aim to understand about earthquakes. So through this simulation, we can get closer than ever before to discover the mystery of one of the most potent and unpredictable forces in nature.
Amazing, Professor. But now we are at the end of this podcast, and I'm very curious. Triggering controlled earthquakes under the Swiss Alps. Can you explain this revolutionary project?
Yes, the Bedretto Lab is an underground laboratory in the Swiss Alps and a groundbreaking initiative. Now, when you think about the Alps, you might imagine amazing landscapes. But beneath these iconic mountains, at a depth of roughly 1.5 kilometer, inside a 5 kilometer long tunnel, there is a revolutionary laboratory. This is the Bedretto Underground Laboratory for Geoscience and Geoenergy, which is run by ETH Zurich and serves as a window to study the deformation in the earth crust at realistic stress and pressure conditions, and is instrumented with state-of-the-art technology. So together with a talented team of scientists from ETH, Aachen University in Germany, and the National Institute of Geophysics and Volcanology in Italy, we started a new project called Fault Activation and Earthquake Rupture. This project is called FEAR. So for this project, I have the privilege of coordinating the modeling working group, ensuring that the simulations and hypotheses align well with our real-world experiments. So what is the revolutionary aspect of this project? So we are attempting something that has never done before, triggering a small earthquake of about a magnitude of 1 under controlled conditions deep underground. This might raise concerns, but let me assure you it's for understanding earthquakes better. Magnitude 1 events are events that are typically insignificant for people, but for us are extremely important, especially if you can do that, if you can analyze and very close to the fault. So by using a fluid injection technique in specific boreholes, we intend to stimulate a tectonic fault and observe and try to control the reaction of this fault. So what we can monitor with something so profound. The Bedretto Lab, with this dense network of various sensors, provide unparalleled conditions. We are not just talking about an event of an earthquake, but the entire story, the build-up, the rapid rupture process, and what happened after an earthquake. So the data we will collect will enhance our understanding of earthquake dynamics, offering intuitions for geoenergy use, and potentially improving the predictability of earthquakes. Now, imagining understanding an earthquake as it happens in real time, recognizing how it begins, accelerate, and navigate through a complex fault network and finally comes to an end. With our sensor in the Bedretto Lab, we will try to track the energy that is radiated during such an event. So questions related to this are what caused an earthquake to stop? What are the specific barriers or complexities in the fault system? And also, perhaps the most ambitious goal of this project is not just understanding, but also trying to influence the behavior of these earthquakes. So through different fluid injections, stress reduction techniques, and other new strategy, we aim to create conditions for an earthquake and then try to control its progressions. So to sum up, the Bedretto Lab project is not just a scientific curiosity, but a genuine attempt to get closer to nature's secrets. By understanding earthquakes for such proximity, we hope to unlock new dimensions in geoscience and geoenergies. And let me say that while the Alps might be a destination for people to escape, well, for us is a journey to understand the Earth better.
Fantastic, Professor. Thank you. Thank you so much for your time and for this interview. And thanks our listeners. If you have any questions about today's podcast, you can get in touch on Chelonia Twitter and feel free to subscribe chelonia.swiss website and be part of the community. In meantime, stay tuned for our next interview.